Good. Then I hope everything works. Let's see. Yes, microphone works. Then I'd like to welcome all of you to the lecture Visual Navigation for Flying Robots. My name is Jürgen Sturm, and I come from the Computer Vision group here at the Technical University of Munich. Before I start, I'd like to show you a short advertisement for a lecture that also comes from our group, but that wasn't on the TUM campus, so nobody knew about it and nobody could sign up for it. But I think the topics are quite related to this lecture here, so if you're interested in these topics, then this might also be interesting for you. It's given by Rudolf Triebel, and he was a postdoc in the Oxford Robotics group with Paul Newman. And there they work on an autonomous car. So this is a visualization of the laser data that they get from this autonomous car, and the car was driving there around. They had a really cool demo in February where the car autonomously drove a particular path and could stop in front of persons and so on. And the lecture of Rudi will not be in particular about autonomous cars, but on the problem of all machine learning tasks that arise from such data. Because of all these signing up problems, the lecture will first start next week Friday, weekly from 9 to 11. So if you're interested in this, then it should be by tomorrow. It should be on the TUM campus, and then you can sign up for it. Topics include probabilistic graphical models, conditional random fields, Gaussian processes, and all kinds of machine learning tools that you might have heard before or not. But in principle, it will be very interesting, and it will be on real data as well. Good. So there is also a website that you can find from our homepage. But yeah, as I said, it should be online as well. Good. Then a second warm welcome to all of you. This lecture will be about flying robots in particular. We brought two of them here. This is the Ardrone. I'm not sure, maybe you've already seen those on Amazon. So this is actually a children's toy. It's meant to be controlled with a smartphone app. So I'll demo that in a second for you. So the idea in principle is that it's a flying camera. So it has a webcam here in front of it, and it streams its data to the phone. And that means that as a child, you could use it to spy around the corner or chase somebody or have fun. And the cool thing about this platform is that the manufacturer released the API to everybody with the intention that people would create cool quadrocopter games with it. And actually on the app stores you can really find interesting games for it. And but this also meant for roboticists, of course, that there was in no time a driver for ROS and the tools to use it under Windows and Linux and so on. And this is also the reason why we chose to use it. It's really easy to fly. In principle, you can give it to somebody and you can immediately fly it. And that's a good prerequisite for starting autonomous flying projects. Wait, so I have to start the... I have to connect first. Let's connect it. Good. So here we go. So it connects over wireless, streams the video, then you can see where you're flying to. And so. Whoop. I might not be the best flyer for this thing. Whoop. So in the summer, this really gives you a good breeze. And so as I said, the cool thing is it's in principle, a wireless webcam, and the cool thing for us is that we can use the images that we're getting immediately to for solving computer vision problems. Good. So far, So good. So let me first start with a few slides on the organization of the lecture. As you noticed, the lecture starts CT, that is 15 minutes after 10. Here we will have a normal lecture with slides and discussions about the material, and then I will give the lectures normally. And then on every Thursday we have either a lab course or an exercise course every other week. The idea is that we give you exercises to solve, and every other week we provide you with programming help to really get it running on the quadrocopter. The teaching assistants for the lab course will be Jakob Engel, who sits over there, and Christian Kell, who is probably at the moment at Aztec to repair our other quadrocopter. Yeah. So if you have questions then regarding the lab course, please address them to Jakob. Now, the first thing, who are we actually? Well, as I said, we are the members of the computer vision group. We have one professor, Daniel Kremers, 3 postdocs, including Rudolf Triebel now, who will give the other lecture. He joined our group in the beginning of April, and 11 PhD students. And we work on a lot of different projects, including motion estimation and 3D reconstruction. That's more or less what people working on the quadrocopters are looking at. And then we have also people working on image segmentation, 2D image segmentation, on all kinds of optimization problems and shape analysis problems. And in particular, my research goal is when I joined this group, so I should say my background is robotics. So I did my PhD on manipulation robots. And when I joined this group, my intention was to look at what methods actually exist in computer vision that have so far not been really applied to real-world problems, in particular to real-world problems on robots. And this is my research focus, so to speak, to see what methods, existing methods, we can extend so that they become applicable and do really cool stuff with them. So next question is, who are you actually? Because I saw from the sign-up lists that we have a quite diverse audience now. Maybe you can just raise hands. Who of you is a bachelor student? Oh, okay. And so everybody else, I assume, is master student. Can you raise hands? Okay, that's good. Last year we had, I think, 5 bachelor students, and I think it was pretty hard for them to follow it. But it was still possible, so in case that somebody didn't dare to show, raise his hand now. Other question is, what are your studies? I think there is a robotics specialization, right? Who's doing that? Okay, so that's roughly half the group. Do we have people from mechanical engineering here? Okay, electrical engineering? Okay, 1. Mathematics? No. Okay. What are you doing? What? Informatics. Normally, yeah, sure. Yeah, forgot about that one. The most common type. Who's doing informatics? Okay. So that means mostly. Actually, we're not so diverse then as I thought from the signups. Good. Also good. That makes it probably easier. Okay. As I said, the goal of this course will be to provide you with an overview of the problems and the approaches that are applicable to autonomous quadrocopters. And there will be a very strong focus on using cameras as the main sensor. I mean, people use everything like GPS, lasers, and so on. But we will mostly focus on methods that rely on a camera. I later show you why it makes sense to use a camera. And in principle, this lecture is located in between computer vision and mobile robotics. And as you already saw, or as you will see in the lab course, you will really use these quadrocopters to implement small navigation tasks. Good. There is a course website that contains everything in principle. So this is the first address that you should look at if you're looking for something. It contains announcements if dates change or something. It contains a schedule. It will contain all the slides as PDFs. Usually I try to put them online one day before the lecture that you can download them or have a look at them if you want. We will also, as you've noticed, we will record the lecture on video and then put it on YouTube so that in principle you can watch it later. Although, of course, it will be more interactive if you still come to the lecture, so I hope I don't lose you by doing this. And the exercises will, of course, be also on the website. This is the second year that we give this lecture, so you this means that the worst errors are already removed from the slides, but it can still be that there are some problems in it, and then I would really ask you to let me know if you find something, or if you think it's going too fast or too slow, or whatever, then please let me know, because there is no reason why we can't change this during the course. Good. Then, if you want more material that goes beyond the slides, I recommend 2 books. Both of them are in principle available online. I think this book is on SlideShare somewhere, and this book is anyway available as a PDF file, so you can just download it. And both of them are really good books. And a part of the slides are actually based on material from these books. Good. So this gives a large overview on the course. Topics might still slightly change. But in principle, the huge idea is that we start in the first weeks with the basics on mobile robotics. It includes in particular, next to a rehearsal of geometry, basic geometry that we'll do next week, we'll look at sensor and motion models, at state estimation and control. That means in particular Kalman filter and PID controllers that some of you might already have seen. Then there will be a week where no, wait, I'm not exactly sure about this. This might slightly change, but there is one week where I'm not here, and then we will see that we invite researchers from related areas to give talks about their recent work. Probably Friedrich Fraundorfer from remote sensing, the remote sensing department, and other people. Maybe also Jakob will give a talk on his current work. And the cool thing here is this is not relevant for the this will not be relevant for the exam at the end, but it will show you where people are actually working on at the moment. So this really connects you to what the current problems are. And then in the second block, we will look at all kinds of problems related to camera-based navigation and localization, which starts by feature detection and matching, estimating the motion of the camera, localizing and building a 3D map, finding correspondences, doing 3D reconstruction, going large scale, and so on. And then towards the end of the lecture, we will look more at higher level problems like navigation and path planning, exploration in unknown areas, and lastly on the evaluation and benchmarking from a scientific point of view. How do you actually know that an approach is better than approach that we had before? Good. We already had that. In principle, the lab course will be given by Jakob and Christian. It will be in room 0514. So this is when you leave here to the left. It's exactly where the stairs, where the upcoming stairs end. And this is a large room with computers, but we also made sure that there are enough places for laptops. So as I said, there will be exercise sheets every 2 weeks, or you're required to hand them in every 2 weeks. And then Jakob and Christian will do a discussion of the homework. And this is the only thing where your participation is really, really required. So we will have attendance lists, and I mean, if you miss once, yes?
What if you can't make it for some reason?
Oh, that's very bad, because that's the whole idea of a lecture and a lab course, that you have time to attend it. Yeah, so if you can't make it, then this is bad. This is the only condition that we have. Yeah. The lecture, I mean. Yeah, I mean, if you have a second lecture, for example, during that day, then you'll have to choose which one to pick. Yeah, as I said, the lecture in principle is not required, but I really recommend it because this is the easiest way to get the knowledge. But of course, you can also have a look at the YouTube channel. Good. And then in the weeks without exercises, we have a robot lab, which means that Jakob and Christian will be in the lab over there and help you with programming. It's not required, but you'll see it makes a lot of things easier if you come there and you just ask them. Otherwise, you can spend hours and hours for figuring something out that's not really the problem. Good. Yeah, the cool thing about the exercises will be that in the first half of the semester, we will teach you to use the quadrocopter. So there will be 3 exercise sheets, and they gradually will build build up your knowledge about how to get the images, how to fly it, how to steer it remotely, and so on. And after these 3 exercise sheets, which will take the first 6 weeks, you will propose a mini project that you will then pursue for the rest of the semester. And this comes then with 3 small presentations that you have to give. To propose your project and to show the progress, and then a final presentation. But really short presentation, so making the presentation itself shouldn't take too much time. Good. The deadline is always before the lecture, which means Tuesday, 10:15. And you're supposed to hand it in by email to this email address. It will also be on the exercise sheets. Good. Then the thing is that we have 5 AR drones, so these things here. Actually, 2 of them are of version 2.0 and 3 of them are of the previous version. In principle, for the exercises that we do, it doesn't make a difference. So the driver should be transparent to these things. The idea is we have 30 students, at least 30 students admitted to the course. So we would like to assign you to teams, or that you assign yourself to teams, which means that we have 3 students per team. And maybe you can do this after the lecture. So this is the assignment sheet. I'll put it up here somewhere. So think about with whom you want to join to form a team. And then to make it a bit easier for you to find a time slot when you can really have access to the quadrocopter, there is also a robot schedule here where you can fill in your team name and choose a particular date that you want to do. It's not strictly, you're not strictly required then to come exactly then, but during this time period you will be more or less guaranteed to have access to the quadrocopter. Good. So we have, as I said, we have lab computers, but you can also bring your own laptop, and that's actually what we recommend, because then you're more flexible with what software you install and to access it and so on. Lists for the groups and robot schedule is over there. The thing is, you have to sign up for this before. Oh, so we have 10 people, I think, on the waiting list for this course. And the problem is that we can't admit more people because then our robot lab will be too full. But from the experience from last year, I think that there is a very good chance for everybody who's now on the waiting list to still get in, because there will always be some people who fall off after a while. So if you're already deciding now that this is not really what interests you, then maybe you can already remove yourself from the list on the TUM campus side. If not, we will open the list for everybody who has not a place so far. So make sure that you sign up before May 2nd. And everybody who's on the waiting list, just do the exercises as you would if you would be there. And then after May 2nd, you will know for sure whether you have a place or not. But chances are really good, I think. Good. So lab course starts this Thursday, and we have learned a lesson from last year. We will start with an introduction to ROS and the Ardrone. So last year we just said, this is the exercise sheet, good luck. Deadline is in 2 weeks, and that was a bit difficult for some people. So this year it will be much easier. Jakob and Christian will show you exactly how to get started, and will demo that to you. May I ask, how many of you have experience in ROS or have seen ROS before? Okay, quite a few, that's good. But for everybody else, don't worry, it will be all demonstrated to you. And then, if you have your own laptop, then it would be a good idea to already install ROS on it, because it's a gigabyte or something that you have to download and could take a while when you're doing it in the lab. And if you want to use the lab computers, then everything will already be pre-installed, and we have wireless sticks for them. And then Jakob and Christian will provide you with user accounts. Yes? Fuerte. I think we have everything under Fuerte. But yeah, that's Jakob. Yeah. Okay. Good. Good. And then, before we start, one warning. In principle, quadrocopters are dangerous objects, so we'll also put up this sheet in the quadrocopter lab. Read the instructions carefully before you start. There is also this protective hull, and it turned out to be really, really useful. So always use the protective hull. The idea is that in principle, when you fly outdoors, you can remove it, or you can have a special outdoor hull that has less wind resistance. But for indoor use, it's much safer and much more comfortable to use this one. Also, if somebody gets injured, then please tell us that we can take measures, countermeasures that it doesn't happen again. I should say, so far we didn't have any injuries last year, so there is no reason to be afraid of it. But still, if something happens, please let us know. Also, if something gets damaged, which can in principle always happen, like rotors can break, or I don't know, batteries can lose capacity, for example, after a while, then tell Jakob and Christian that they can replace it or that they can fix it. You should never touch the propellers, as you've seen. I already had my hand in it. It does not really hurt, but nevertheless, try not to do that, because in principle you could get hurt. Also, of course, don't look at it and then switch it on and so on. Things that you should know, but yeah, good. And then also don't worry about the quadrocopter. If it does something strange, then just let it fall. Don't try to catch it because you might hurt yourself. Yeah, good. So far, so good. Then, this is our agenda for today. I'll start with a brief history of mobile robotics, and then I'll give you a brief intro to quadrocopters, why they fly, and so on. And then we'll talk briefly, depending on how much time we then still have, on paradigms, programming paradigms in robotics and how they changed over the years. And we'll briefly look at architectures and middleware in general, which will then be come in more detail in the lab course on Thursday. Good. First, maybe not so important information is where does actually the word autonomous robot come from? Well, autonomous comes from automaton, from Greek, which means self-willed. And then the term robot was invented by a writer, Karel Čapek, actually his brother, who suggested this term while he was writing a play. And it comes from the Czech or Polish word for robot, for labor, sorry. And actually the first term that Karel Čapek was intending to use was labori. So, if he had chosen this word, then maybe he would call the robots now laboris. And yeah, it just means workman or hard work, something like this. And then the same for computer vision. Actually, when the whole thing with computers started, Marvin Minsky, who is one of the grandfathers of artificial intelligence, told one of his undergraduate students, so like students in your age, to solve the computer vision problem, essentially to spend the summer linking a camera to a computer and getting the computer to describe what it saw in one summer. And that then ended up to be more complicated than expected, and we're still working on it. No, but it's interesting to see how easy it can happen, even to people with bright minds, to underestimate the complexity of a problem. Good. So the history of mobile robotics then roughly started at the same time. So this is the Stanfort Cart that was built in the 60s. It's really a small cart with 4 wheels, and in the beginning people just remote controlled it, and then added more and more autonomy or components to it. Even remote controlling the car turned out to be very complicated because there was a delay, of course, in the commands they gave to the vehicle and the actions that it performed. So at the first stage, it just they found that it was really difficult to keep the vehicle on the road, and then they had a computer program that could predict where it would drive to, which made it easier for the operator to adapt, to already foresee what will probably happen. And then after a while, they added also cameras to it that they autonomously that they used for obstacle avoidance. So here you can see the cart. It's taking 9 pictures of the room. So it's a bit hard to see, but there is a camera and it's moving from right to left here, taking different pictures at different positions. And then it extracts so-called interest points, although at that point the idea of interest points was not yet developed, to compute the depth of particular points in the scene. And then with these points, the robot could already determine where the obstacles are and where it could drive through. And then in this way, it was able to traverse this room with obstacles in it in the 60s. Right, but the whole procedure here took 5 hours, because of taking the images and processing them and so on, and probably it was also not extremely reliable. But nevertheless, it's interesting to know that the beginnings of mobile robotics and all of these kinds of problems that we're still working on have already been looked at in the 60s.
I have a question.
Yeah.
Flashing movie, is it a studio flash system?
I assume that it's a flash. It's a real flash because probably the camera was not too sensitive. I assume. I have no idea.
Yeah.
I mean, this is really sped up by. Yeah, that's a good question. But I assume that this is automatically. But I have no idea. I mean, maybe not. Good. And then roughly at the same time, people built Shakey the Robot. And this is a really famous robot because it had a lot of impact. It already had drive wheels and a caster wheel. So it's quite similar to other robots that we have today, like the Turtlebot, for example. It has an onboard computer, or what at that time people called a computer, and it also had a television camera and antenna for the radio link, range finders for it, and with that it could already do pretty cool things. So unfortunately the sound over the speakers doesn't work, so I will have to commend it. So this is the robot driving, and it could already move from A to B. It could localize itself in the world. For that, there were some strong assumptions here to make that work. So there was only white and black in the world. And black means obstacle, and white means free. But nevertheless, they so to speak, define some of the problems that now still have to be solved. So you could give simple commands like go to a particular position, or turn left, turn right, move forward, and then it could do that. And by having obstacles like this, it could also then find a path around it by adding intermediate sub-goals. You see also where the name comes from. So when this robot moves, it really shakes a lot. So this is a simple path planning problem. I assume this rectangle here looks so clean that probably somebody typed in where the obstacle was, and then the program was generating sub-goals around it. And then there is one nice scene that you should definitely see. It could also push boxes to change the environment. And things like that. So at that point, they used symbolic methods to compute it, and it's the noise that changes something in the world. So they already had a notion of noise, but it was relatively controlled and executed by a person. But nevertheless, very impressive for this time. And then in the years later, this got more solid, of course, and then also the industrial industrialization of robotics took place. So a lot of the production was moved to robots, but still using kind of the same concepts that you can foresee all things that happen in the environment, and that you take that you hard code, so to speak, what to do. And then it took really decennia before this was before the next level, so to speak, came up of robots. So this originated from the University of Bonn and Carnegie Mellon University, a so-called tour guide robot, or a robot that you could place in a museum and that would move people around. in contrast to Shakey, I mean, in principle, it has the same mechanical architecture, but a huge difference was that there was no longer this assumption of a closed world, and that you really know what is in the world and what is not in the world. So here, really strange things happen. Yeah, okay. Suddenly you have children, and they really have strange ideas. There is also the problem that you need to communicate with people, so that people started to think about human-robot interaction. That you need to add displays that somehow show people in what mood you are, and for example, if they are blocking your way, then you can really look angry and shout at them. And this robot even bumped into people at some point, because sometimes there were crowds of people standing around it, and it couldn't get through. And then, you know, it started to shout, and then it was moving against people to make its way. And this robot, or one of these robots, is actually in the Deutsches Museum here in Bonn, in Munich. So if you're there in the robotics section, then you can still see it. Good. And then this technology, or these ideas, were further used in products then, which took another 10 years roughly to develop that. This is the Roomba that all of you know, I guess. Or I should say, no, this robot doesn't have any advanced control architecture. It has, because it also lacks any sensor, it just has one contact sensor, and when it's actuated, then it changes the direction, and it anyway changes the direction occasionally by moving around. So what you see here is a long exposure picture. The robot cleans your living room, for example, and then you have a small LED on it, and then this is the way how they took this picture, and you can see that although it's covering everything, it's not really efficient. You know, a path like this might not reach all spots, but it might clean 10 times the same spot. But then, a few years ago, this robot came out from Neato, and it already does. So it has essentially the same technology as this tour guide robots. It has a laser scanner, a rotating laser scanner. Or a similar version of a laser scanner, and it uses that to create a map of the environment, to know where it is and to know where the obstacles are, and then on top of this map it computes a coverage plan that will move it ideally to all spots. And you can see this is of course much more efficient and much more guaranteed to get all dirt. Also, it's still not a perfect substitute of manual vacuum cleaning. But this is quite impressive. So we are now at a state where things like this can work in uncontrolled environments at a reasonably low price. Good. Then on the research perspective, there was the grant challenge. It first took place in 2004, but then nobody actually made it. Or the idea is that a car drives autonomously through the desert on a 150-mile-long tour that was specified by GPS coordinates, but because GPS is not accurate enough, you can't just blindly follow it, and you still have to evade other vehicles and potentially other obstacles. And so in the first year, all of the teams failed. The last team failed after the first 7 miles. It just got stuck somewhere. And then in the next year, so nobody won the prize. And then in the next year, they had it again with a even more complicated tour. And then already, I'm not exactly sure, 5 or 7 teams succeeded to finish it. And the Stanford team won the competition. I think it still took 7 hours or something to complete the 150 miles tour. And this showed then that in principle you can have cars that can drive autonomously. The year after, there was this urban challenge where cars had to drive through a city. And this is actually the origins of the Google car and all of these autonomous cars at the moment. So this really stimulated the development of autonomous cars. And we're not yet there, but it's foreseeable that in a few years, autonomous cars will become more a reality. And then at the same time, in industry, also interesting developments are happening. What is it? So this is the Kiva robot system. I'm not sure whether you've seen it. So this is used for warehouses. In particular, these robots can go under a shelf of products, spin around it to move it. Or to carry it and then bring it to a worker that then puts products into packets. This company has been bought, I think, last year by Amazon because if you have technology like this, then this saves lots of costs in delivering goods to people. But still, as you can see here on the floor, or maybe I should rewind it for a second, it's not completely autonomous. You have to change the floor. So you see here certain lines and magnetic or some wires in the floor that will keep the robots on track. But nevertheless, it's interesting to see that this scales. So they have thousands of robots in a warehouse. And then, at such a large scale, you also know very exactly about all the failure modes that can happen, what can break, and so on. Otherwise, if you have just one robot and then it breaks every 2 months, then you can't really have statistics about that. Good. And this is moving even further here with autonomous forklifts. And things like this happen at the moment everywhere in industry. So robots are getting autonomous and they don't need, or they need less and less these guiding lines or guiding wires in the floor. And this saves of course lots of much money if you have that. Good, and then we now finally come to the quadrocopters, which started roughly in the beginning of the year 2000. The reason why it didn't start earlier is because quadrocopters are very difficult to fly by hand. I mean, the idea of a quadrocopter has been invented in the 1920s or 40s, I'm not sure. But it was virtually impossible to control the 4 motors by hand. And what happened at the end of the 90s was that the MEMS sensors were developed and small embedded processors that could automatically level the quadrocopter so that the pilot actually just has to think about in which direction he wants to go. And then, first of all, hobbyists started to build quadrocopters like this. There are numerous open source projects where people then attach cameras to it and did really cool stunts. And I should say that still most of the quadrocopters, of course, are manually controlled or manually flown by a pilot. And then, I mean, these are spectacular movies, and some people even wear special goggles to get a first-person view of the quadrocopter, and then you can do really cool stunts. And I think also parts of so it's also used in the filming industry now exactly for such stunts. I think parts of the James Bond movie were recorded from a quadrocopter. The reason is that with a quadrocopter, with an unmanned vehicle, you can do much cooler stunts without having to worry too much about the safety of your pilot. In the worst case, your quadrocopter breaks, but it might be worth the special effect, of course, for the movie. And then, roughly 10 years later, the first autonomous flight movies came out. So this was a pretty amazing work from the GRASP laboratory at the University of Pennsylvania, where they showed that you can do really impressive stuff on the control of quadrocopters. So this one does flips. However, it requires external tracking of the pose. So there are cameras all around the cage. These cameras that track the position of the quadrocopter at 500 hertz or at 200 hertz. And then you have an external PC that computes control commands and that plans the trajectory, and that then sends them to the quadrocopter, and the quadrocopter just executes it. But nevertheless, this inspired people to, I mean, when you see these movies, you think, how much more would be possible in this respect. So they flew through windows in all kinds of orientations, and in principle, the important thing here is that it would not be possible to fly here in a static motion. The quadrocopter can't stand in this orientation, right? Because it can only produce thrust downwards. So you really have a good motion plan if you want to execute something like this. Could also land on the wall and so on. And then they even extended this further by adding a small gripper to the quadrocopter, that it could lift these things. Of course, they have to be super lightweight. But nevertheless, and then they were able to show that you can build simple structures with this. People from ETH, so this is still from University of Pennsylvania, but people from ETH used that to build a large wall made of sponges. I mean, it has to be very soft and lightweight materials. But in principle, this shows that you could have aerial manipulation, that you could use a large group of quadrocopters to build up a tent maybe, or any other construction. I mean, not with these robots, of course, but that in principle this would be feasible. Good. So at the end here you can see how 4 of these robots together constructed. So there is always one robot picking up an object, and there is a waiting position here, and then they go round and round. So in principle, you could have tens or hundreds of robots doing the same thing. You could also use them, for example, to clean up a park after a music festival. You could have a large group of quadrocopters flying out and then collecting all the trash. Of course, then there is this other problem that the battery only lasts for 10 minutes maybe. So every 10 minutes you need to recharge, which is another open problem. But nevertheless, pretty cool. And then also people use this to map or create autonomous maps from buildings, for example. So this is the Pelican quadrocopter from Aztec that we also have. And it carries a Kinect, I think, at this time. This was, so to speak, this was a collaboration between one team who had the quadrocopter and autonomous flight, and another team who had the mapping software. So here you see a matching between visual features to create a map. And then at the end you get a point cloud out of this. This is Arvis for those of you. You will use it in ROS. This is one of the standard tools, and you can see a graph being built up and points from the Kinect being assembled into a large point cloud. And this is really cool. For example, for architects, if you have a device like this, you could fly through a building and then get out a current version of the map. I mean, still these maps are not what an architect would need, but at least they give you the impression that in principle, with more work, this could be very cool. And then we also started here. I joined the lab exactly 2 years ago around this time, and then we have a couple of own works in this direction. We have people working on visual odometry, that is the motion estimation or the motion of a camera, where Frank and Christian, for example, Christian is now here, this is Christian Kell, work on. We have camera-based navigation. This is mostly what Jakob has been doing, and we're working on 3D reconstruction, which has been done by Eric. And this is a nice video that we took also 2 years ago. This is the result of Jakob's master thesis work. So here you can see the Ardrone at the TUM Open Day. And the cool thing is, because it's so lightweight, it's relatively safe to be used with people. With the Pelican, you would have to worry more. Here it uses the forward camera to estimate its position with respect to a map, and it always flies back to some spot. And this is, looks nice, looks cute. And you could of course think about what other abilities you could add to this. Once you have position control, you can think about path flying. You could follow a person. And maybe even have small manipulation tasks. So we've been thinking about adding a gripper to this, and so on. And good. And just to give you this is a personal view of current trends in robotics that we are seeing. And so as you've seen now in these videos, robotics is really a field where a lot of things happen and where a lot of change happens. And there are still entering new domains. I mean, industrial automation is at the moment being revolutionized by these more flexible robots in contrast to the industrial robots that we had before. We have also domestic service robots for vacuum cleaning and lawn mowing. There are surgery robots. Not sure whether you've seen the Da Vinci robot, for example, that doctors can use to do really small surgeries. There are, of course, lots of toy robots, especially in Japan. And autonomous cars is another hot topic at the moment. And then, of course, aerial everything. Aerial monitoring, inspection, construction, and who knows what. Good. Then I have to change to the second presentation. There were too many videos in it. Good. And then, in particular, with respect to what we want to do, there is also an increased interest in flying robots. So at the robotics conferences, you always see quadrocopters, and you see people trying to apply their stuff to robots. Because it's cool on one hand side, but it also shifts the problems. So a lot of people have focused on mapping and localization in 2D, because when you have a car or when you have even more extreme, a mobile robot on a factory floor, you know that it will always be on a plane. There is no way how it could be ever, at a different Z coordinate. And doing things in 3D is more difficult. On the other hand, some problems get simpler. For example, if you have to generate a path through the air, then it's usually obstacle-free, in contrast to a robot that has to navigate through a crowd, which might be more complicated. And quadrocopters, in contrast to other flying robots, have a few advantages, and this is the reason why we use them. They can keep the position. That's very handy if you debug things. It can just stay in place. It's relatively reliable and compact. For example, in contrast to a helicopter that has a large rotor blade, it's difficult to grasp it or hold it. And they have relatively low maintenance costs because there are no parts that you need to exchange. And it's also relatively cheap to buy. So in case that somebody of you wants to buy one of these by himself, these things are sold, for example, at MediaMarkt for €300 or at Amazon. And there is an ongoing trend towards miniaturization. So this is another quadrocopter that I wanted to show you. This is how's it called again? Something with B. And it also corresponds to the sound that it makes. It sounds like a mosquito. It's much smaller and even less dangerous, of course. But the ladybug, right. It doesn't have, so the only thing that it can do at the moment is to be remote controlled. It can't keep the position. It will always drift in one direction. But nevertheless, we found out that it can carry 10 grams additionally, or 5, maybe just enough to add a small wireless camera, and then in principle we could run the same algorithms again off board and do all the cool mapping stuff. But this is still an open problem, and if somebody of you is interested in trying things out, so we are always open for people who want to do projects outside of the lecture, play around with AR drones or with this one or with our larger quadrocopters. So if you're interested in something like this, then please talk to us. Good. And then just to give you a few ideas what this can be used for. As I said already, it's really cool to use quadrocopters for recording stunts of action movies or photography and so on. It would be always cool to have this as an autonomous application. At the moment, as I said, you always need a pilot that gives the steering commands. And depending on a quadrocopter, it needs to be a skilled pilot, especially when you put a heavy camera on it. So all of these applications need, in principle, autonomous or would benefit from autonomous robots. There are search and rescue missions, like after an earthquake, when you're not really sure whether you can go into a building or not, then a quadrocopter might be the least immersive. It's also easier to path planning is easier because the air is always free in contrast to the ground. If you go in with a ground robot, then you have to deal with all kinds of problems. There could be rocks in front of you and so on. Or you could drive over a victim, potentially. Aerial photography and photogrammetry is another problem, interesting application. Documentation of scenes. So I think there are companies already that sell quadrocopters that the fire brigades can send to a place where when a building burns, or for a police use. For example, you just have a flying eye, so to speak, that you can send up in the air, and it will stay there for an hour and give you aerial images. Other applications are to inspect bridges and buildings from the outside. So as you know, every bridge has to be checked once a year, and depending on how accessible it is from below, this is a major effort to do that. But if you had a easy-to-fly quadrocopter, then you could just use that. Construction tasks is a bit into the future, I guess. The military uses it, and you have to be aware that the technology by itself is also used, or partially also comes from the military, and will eventually end up there again. So you have to really think about what your attitude towards this is. As I said, most quadrocopters in all of these applications are still controlled by human pilots. Good. I already mentioned a few commercial platforms. We use the Parrot Ardrone. There are also a lot of open source projects like the Microcopter, which is probably the most famous one. You can buy all the parts there and then assemble it yourself. For us, using commercial platforms has the advantage that we can start immediately at the point where we want to get started. If you start with a microcopter, then you're busy for a few weeks to assemble all the parts, and then there is no guarantee that it will actually work. Good. There are, as I said, different flying platforms or flying principles. Most common one, of course, is the fixed wing airplane that generates the lift through moving forward, and then there is the special shape of the wings that generates a thrust upwards, and the flying direction and so on is controlled by small flaps on the wings. The disadvantage here for a roboticist point of view is that it always has to move. It can't stop, and that makes path planning and everything more complicated. It also needs a minimum size environment. You can't fly in an arbitrarily small room, of course, with an airplane. Helicopters are also popular. You've seen probably also the toy helicopters that are sold. The problem with the helicopter is that it's more complicated to control it. Also, this is also getting better now with the MEMS technology being built in. So usually flying a helicopter was possible manually, but you need some training for doing that. I'll show a picture of this later on. And then we have a quadrocopter, and yeah, show you more of this in a second. So this is a picture of a helicopter. It uses this so-called swash plate, which is a relatively complicated mechanical construction that will change the orientation of the rotor blades, depend as a function of the position of the rotation angle of the main plate, and this allows you to generate different thrusts in different directions, and in this way you can move forward and sideward and so on. And there is usually a tail rotor that allows you to change the yaw angle of your helicopter. And I mean, this is possible and energy efficient, and this is why it's used in practice a lot. But quadrocopters are in all respects easier to use. So this is the Ardrone, and this is a schematic top view. We have 4 motors or 4 propellers, and all of them ideally rotate at the same speed. Always the two ones opposite to each other are rotating in the same direction, and the other 2 are rotating in the opposite direction. This means that the torque of all the 4 rotors is sums up to 0, which means that the whole platform doesn't start to turn suddenly in one direction. This is why we don't need a tail rotor here. And then all of the 4 motors in principle generate the same thrust, and that means that the quadrocopter is accelerated upwards, and then if this exactly matches the gravitation vector, then we keep the position. And to ascend, then you can increase the speed of all motors equally. To descend, you reduce the speed of all 4 motors, and then you will fall down again. To turn left, you can decrease the velocity of these 2 motors, for example, and then and increase the one of the right-turning ones, and that will, as an effect, move the quadrocopter or start turning the quadrocopter to the left. And you can do the same, of course, for turning right. And to move forward. So, I mean, so far the quadrocopter was perfectly balanced. To move forward, you can give a higher thrust to the back rotor, and that will. It's maybe not the best way to show it here, but if the thrust of this motor suddenly is higher than the thrust of this motor, then the quadrocopter will tilt in this direction, and because it's then still outputs a certain thrust, it will accelerate in this direction, and same for the other direction, of course. And you can also use that for flying left and right. If you increase the thrust of this motor, then this side will come up and then accelerate in this direction. Yes?
Going to lose height while this?
No, in principle, because you have. Should be probably. Probably you'll have to compensate for that somewhere in the control loop. I have to say, I'm not the expert here on this part of the control loop, because this is already built into the platforms that we have. But in principle, part of the thrust vector then goes, if you split it up in 2 components, and we'll look at this later on in more detail. I'll do it here. So normally you have just a thrust vector like this that moves up, and when you're slightly tilted, then you can say that only part of this vector is still there to compensate for the gravity, and the other part will move you forward. So probably you'll have to adjust for that as well. Good. This is exactly what there is a low-level problem of keeping the attitude and to stabilize the robot to compensate for disturbances when one of the motors, for example, is not doing what it should because it's you have to compensate for this, and we will not cover this in this lecture. If you're interested in this, then there is a group on flight dynamics, Professor Holzapfel in mechanical engineering, and they have a number of really good lectures on this, I heard. So we will more focus on the high-level part, or that what we call the high-level part. That one person's high level is the other person's low level stuff. So we will look at how to compensate for the drift using a camera, how to avoid obstacles, how to do localization and mapping, how to navigate to a point, and so on, and returning to a takeoff position, and so on. So we assume that we already have a platform that doesn't fall out of the air, but a platform where we can already command forward velocity, leftward velocity, rotation velocity, and so on. Good. The general challenges of using quadrocopters are that, of course, the payload is limited in contrast to a wheeled robot. Even a wheeled robot has some payload limitations, but it's even more extreme on the quadrocopter. You can only carry 100 grams, maybe 500, depending on what platform you use. We are actually involved in one research project where we have a quadrocopter a microcopter consisting of 8 rotors that has a weight of 5 kilograms. And then you can, of course, take more sensors with you. But even in 5 kilograms, you have to make sure, or you have to decide on what you can take along and what not. For example, there is no graphics card on board. Good. And then, of course, also the battery life is limited. Also, depending on the size of the quadrocopter, it can have really fast dynamics, which needs an electronic stabilization at a high frame rate. The thing is, the smaller the quadrocopter gets, the more fast the dynamic will get. So while a large quadrocopter doesn't easily flip over, it can easily happen with this one. And then there is, of course, this problem with the safety. So it helps, of course, to add mechanical safety shells. But I think, or we think that the only way to really make it safe is to make it so small that no matter what happens with it, it can never hurt anybody. But nevertheless, it's an important problem. And then I already mentioned this with the potential use for military applications. You really have to think about where the responsibility lies, and I think even as a programmer, but definitely as a scientist, you also have to take over some of this responsibility, and you have to be sure to what you contribute actually, and to be aware of what you're contributing to. You should also think about where is the human in the control loop and who's actually taking the decisions. And then depending on the product that you're working on, the society, of course, might change. So what is the effect when you build a vacuum cleaning robot? What will that do? And I think for a vacuum cleaning robot, the effects will be positive, but there might be other robots that, especially in the military domain, where it's not so clear what the benefits are. And then the last question is a bit into the future. Of course, can you, when you develop things like that, how can you make sure that it behaves in the way that you want it to? And then there is the famous 3 laws of robotics of Asimov that I guess most of you will have seen some before. The question, of course, with these laws is that it's not clear how to integrate them at the robot at this point. But nevertheless, I thought it would be interesting to put them up on this slide. Good. Okay, now after all this preparation, imagine you want to build a robot that does a particular task, say a navigation task. How would you tackle that? So what hardware would you choose, and what software architecture would you choose? And to give you some concepts, here people usually distinguish between sensors and actuators and the control software in the middle. So let me ask you, what sensors do you know? And what actuators? Any ideas? Yes.
GPS?
Yes, GPS is definitely one. Yeah, all good. Yes, yeah. Ultrasound as well. Exactly. So I should maybe say that most of these sensors are already here integrated. So we have ultrasound, actually. There is built-in gyroscope and the accelerometer. The accelerometer, the gyroscope is used to estimate the orientation of the quadrocopter, and the accelerometer is used to compensate for the drift of the gyroscope because it's not super accurate. There is also a downward-looking camera that compensates again for the drift of the platform by itself, and a secondary camera that's looking forward, that's only there for fun or for us to do cool navigation stuff with it. The autonomous cars, or also the most wheeled robots, use laser scanners. So this is a 2D laser scanner. On the Google car, there is a 3D laser scanner. There is one company that's most famous for it that sells the Velodyne. Other sensors include, for example, the Kinect, that's also composed of a projector and an infrared projector and an infrared camera. GPS was there, also very useful. Good. And then what kind of actuators do you know? Yeah, but the motor by itself is not an actuator.
Grippers.
Grippers? Yes, yeah, a gripper. Also things like a joint. True, for a manipulation robot. Yeah. Good. And I mean, in principle, yeah. The motor and the gears and so on that move here the quadrocopter. And then there is this control. There is always a PC, or sometimes even several PCs that run software on it that form the control unit. Good. So this is a very coarse view on the paradigms and the paradigm shift in robotics. In classical robotics, and this is what you've seen with Shakey the Robot and the Stanfort Cart, people assumed, I mean, you have to get started somewhere, so people assumed exact models and more or less no sensing or very limited sensing. You know, that there is exactly one thing that you need to observe, and you observe that, and then you generate a plan. And then it turned out that this doesn't really scale to the real world. I mean, of course not, because you can't foresee everything outside of the laboratory. So then people like Rodney Brooks came up with reactive paradigms, where they just said, you know, we don't need any complicated models. We just will start like an insect more naturally, that we have very simple behaviors, and that we will immediately start with the sensors. So everything is linked to sensor observations. On the other hand, it then turned out that this behavioral approach does, again, not really scale to larger problems. Also, it scaled to the real world, but not to really complicated things. And then more hybrid approaches came up that use both of the advantages of both ideas, so that you have reactive behaviors at the lower levels and more model-based behaviors at the higher level. And then there are some trends that I think I have observed at present, which is, first of all, there is this idea of big data that in principle, even with an autonomous car, it's very unlikely that you drive somewhere where nobody has driven before. So there is always, in principle, a map, and there are always other cars that you could ask. The other thing is that you're always connected somehow to the internet, and that you, in principle, don't have to compute all things by yourself. So sometimes it would just be easier to add a communication module to your robot, especially to a small robot like this one, that it can communicate with your smartphone or with a PC, or maybe even with a computer on the internet, that then does the hard computations for you, and it can also take advantage of the big data there. Good. So let me go back to the classical hierarchical paradigm. This is inspired from methods from artificial intelligence, where you try to break down a problem into a set of steps, sequential steps. This is also the time when the strips planners were invented. Things like Prolog, essentially, or the predecessor of Prolog, where you specify a set of horn clauses and assumptions about the world, and then you try to come up with a logical derivation of something. So, for example, if you need to drive from A to B, then you do a set of reductions on the statement go to until you come up with a plan that you can then execute. For example, Shakey had to find particular boxes and then move them to designated positions. The same applies to the Stanford Cart. So there was a very strict control program that took exactly 9 images, identified interest points, estimated the depth for them, integrated that into a world model, correlate that to estimate the position, and then determines the direction in which to move, and then execute this, and then start over again. So this is a very sequential program. And if something in between goes wrong, then there was no way to interrupt it, for example. So this is another view on this. And this is actually one of the architecture plots that you will see more often. So usually we have the environment, and that's the robot, and the environment that performs some kind of sensing, feeds the data into some processing architecture, and then generates at the end a control command that will then again change or influence the world state in the environment. So, as I said, the characteristics of these paradigms are that they were mostly symbolic, and that the robot perceives the world or anything it needs to know, and then plans next action, acts according to it, and it integrates everything in a single global world model. That's possible because the problem is so specific that you can come up with a model for this. And this is also what people call, sometimes now, today call GoFi, the good old-fashioned artificial intelligence that really does symbolic derivations. And this, in really large contrast to that, Rodney Brooks developed this reactive paradigm, where he said that it's impossible to scale these symbolic methods to real-world problems, but that very simple mechanisms exist also, for example, in insects that make a cockroach follow a wall, or that, without complicated plan reductions and so on. So he came up with the idea to have a certain set of behaviors that can activate and deactivate each other, and each behavior is based on local sensing, and it generates a certain output. And then combinations of these can solve really complex tasks. And you can compose things out of this. For example, you could have one behavior that just avoids obstacles, and then on top of that, a second one that wanders around, and a third one on top of that that makes the robot wander in particular directions that will hopefully explore the environment. And the characteristics of this is that the robot was suddenly part of the world. So it's integral part of the world. It can't do any useful sensing without interacting with the world. So instead of having one super AI that takes a small observation and then does all its computations based on this, these robots really sense as much as they can from the world, or the people tried to solve the AI problem essentially by sensing. If you have enough sensors, then maybe you can. Then maybe there is no computation problem anymore. So in the extreme case, you would not even have memory. You just so every information that you need, or any knowledge that you need, is stored in the world. And there is a tight coupling then between perception and actions, and everything is local in the frame of the robot. Skip that. So this is one example from Rodney Brooks, where a small robot with a sonar has a sonar sensor, and then it has a module that detects collisions, and when it has collision, it just halts, and that will influence the move forward actuator. And at the same time, these sonar sensors are used to generate a force. When something comes closer to you, it would push you away virtually, and this would generate a heading that is then fed into the turn actuator that will move the robot away. And on top of that, you can. So this by itself will generate a robot that will evade obstacles or avoid obstacles. When something comes closer to the robot, it will move away. And then on top of that, you can add a wander behavior that will generate a random motion to somewhere, and that will influence this force in a way that the robot will randomly walk around. And then on top of that, you can follow or build more complicated behaviors and so on. And in principle, you can see the Roomba robot as being built according to this methodology. So it has very limited sensing, but it's enough for the robot to, whenever it hits something, it will turn around and so on. So there is no world model needed in it, except for changing after a while the direction, or returning after a while to the base to get recharged. Good. Then I'll briefly show you one concept. We will have a look at motion planning and so on later on in the course. But there is this concept of potential fields that are also very simple, a simple means to generate motion commands for a robot. The idea is that we define a potential field for a particular map. You can imagine a potential field like a magnetic field, for example, and the robot will try to follow the field lines of this field. And this field depends on obstacles and the goal where we want to go to and so on. So we design a field beforehand, a virtual field that will move the robot towards its goal. And it can be composed out of different components. For example, you can have a uniform field that will just move the robot forward, independent of where it is exactly. You can add perpendicular fields to obstacles that will push the robot away from obstacles. You can have an attractive potential that will move the robot towards its goal, or move it away from dangerous objects or obstacles again, where you don't want to hit. And using that, this is actually used by lots of robots for local navigation. Assuming that you know where you are, you can look up this this potential field vector, the gradient of this function, and then it will slowly guide you towards your goal. And when there is an obstacle in between, it will hopefully push you away from this obstacle. And in this way you can reach your goal. And the nice thing is that you can, in principle, transform the behaviors that we've seen before into such fields. So, for example, the collision avoidance by itself would add a repulsive field to all the obstacles. The wander behavior would add a uniform field into a random direction, and the corridor following would add certain fields to the wall that make the robot be pushed away from the walls but moved forward inside of the corridor. As I said, this is a very simple method that is often used. It's easy to visualize and it's easy to be built up. But it, of course, suffers from local minima. If you have an obstacle formed like this, then the robot might be pulled into this obstacle, and it can't escape anymore because there is a local minimum somewhere where it gets stuck. So this by itself, and this is another example of why behavior-based models are not enough in a general case. They get stuck as soon as the problem gets more complicated. And this is why you need then a high-level planner that does some symbolic reasoning and finds a way around it. And this is why then in the 90s the hybrid approaches appeared that combines the advantages of both of these paradigms, that you use a world model in high-level planning, but in the low-level, this behavior-based methods. Good. And then, in modern times, robots became really, really complex systems. A quadrocopter by itself alone, I mean, you've seen how many different sensors there are already built into it, and this makes it usually hard to write all the code that you need for flying this quadrocopter by yourself. So you need to take advantage of things that are already there, and this means that it makes sense to have a good robot architecture that makes it easier for you. Good. And yeah, you need different capabilities, and different capabilities for different tasks, of course. And this means that it makes sense to use when you design such an architecture, that to make sure that it's as modular as possible, that you can use different parts in different combinations, that it's robust. So even if you have to rely on a certain module that maybe is faulty or that does not work perfectly, that the system by itself doesn't crash as soon as the first component fails. So actually, in the Stanley car in the Darpa Grand Challenge, there was a special computer running a watchdog, and as soon as one of the computers or one of the processes died, it would respawn it again to make sure that even if there will be definitely over a 5-hour course, there will be definitely memory leaks, there will be definitely problems. So you have to have a way to reset from this. And a good robot architecture allows you to do that easily. It's also a good idea to have it decentralized, that not everything runs on the same computer, not everything is using the same block of shared memory. Very dangerous. A good framework also makes it easy to reuse software, that you have certain hardware and software abstractions, that it doesn't really matter what specific kind of camera you are using on the lowest level. It's also useful for the debugging or the programmer side to have introspection, that you can at all points see what are the modules communicating, is the module still communicating something, and what, and so on, and that you have means of logging data and playing back data. And of course, it also helps if the system is easy to learn, because there will be a constant flow of people, especially at university, but also in the industry, that leave projects and then come new into the project, and then it's an advantage if a system is easily understandable. Good. One of the most important tools of a robot architecture is the robotic middleware that provides the infrastructure that allows for the communication, that provides all of these data logging facilities, introspection, maybe even visualization tools. And there are several systems available. And the most common one is definitely the robot operating system, ROS. It comes from Stanford University and then was adopted by Willow Garage, and since then really improved a lot. And it has now been moved to the Open Source Robotics Foundation that will take care of further developing this. But before this time, there have been other systems like Player Stage. In Freiburg, we've used Carmen a lot, which is based on ICP. YARP is another European platform. Orocos is also widely used if you have to deal with real-time systems like a manipulation robot that has to react quickly. There are also commercial solutions like the Microsoft Robotics Studio, and a few simulators, the VBot simulator, for example, for humanoid robots. So there are different things, usually incompatible to each other, but in most cases there are bindings that allow you to, if you really need to combine them, you can. But for our course, we will completely focus on ROS, and I think this is also more or less a standard now in robotics. Good. As I said, we will have more often architecture plots like this, where we have the robot at the bottom. Then we have need modules, for example, for sensor drivers, actuator drivers. There are certain interfaces that abstract it from the particular properties of this sensor or actuator. And then we might have a localization module that gives the position to a path planning module that will then come up with a path. And the local path planner that will avoid small obstacles. You see there is again this link that is more a behavior than a high-level deliberative planning module that does collision avoidance, and then gives back these commands to the motors, and then the robot will execute it. And at the very top you might have something like a user interface or a mission planning. And for a small robot, this architecture might work, but of course, the larger the problem gets, the more complicated these plots look like. This is the software architecture used in Stanley, in the robotic car from Stanford University. So you see here already there are 5 different lasers. There is the camera, radar, GPS, all of these sensors that we already mentioned. The IMU, wheel velocity, which is called odometry on a car, and also the status of the brakes, and so on, and that all of that feeds into different modules that do pre-computations and so on, and pass on the data to other modules that do path planning and steering control and so on, and then this moves back to the car, the data. And then there are some global services here that do that monitor the status of all of the modules and restart them if necessary, and that log data and and so on, and store data on the hard disk. Good. And even though you might think that a car is much more complicated than a robot, then you haven't seen the PR2 robot. So this is one of the most developed robots at the moment, I would say, the PR2 from Willow Garage. It has 2 arms and a head that it can move. It has lots of sensors. I think it has 7 cameras and 2 laser scanners. One of them can be tilted. And when you just switch on the robot, then it will immediately start 73 programs that just connect to all the hardware devices. And they will publish more than 300 different messages or message channels and provide more than 170 services. So just by doing nothing, essentially just by being switched on. And then on top of that, you want to do something cool like cleaning up a table or making pancakes, for example. So there are many more nodes than on top of that. But this means that the whole thing is really complicated to understand why something fails, and then you need really good introspection tools that allow you to quickly figure out where the problem is, to know which sensor you have to replace or which module maybe doesn't run anymore. Good. So there are some general communication paradigms, and most of them can be found in ROS and vice versa. But this is just to show you the basic concepts behind ROS, but in principle they also apply to other robotic or in general to middleware. So typically there are two different things. Either you can have a message-based communication, which is by default asynchronous. So one node or one program can send a message out to another program or another computer, and then this one will get it at some point. The alternative is to have direct memory access, that both of them write to the same memory. This is of course much more efficient, but it can produce all kinds of problems when both of the processes try to write at it at the same time. So there are different forms of communication. The push form means that one process is sending out a message. The pull means that another process is asking for data. There is publisher-subscriber architecture where you have, I'll show you that in a second. There is this idea with the blackboard or the shared memory. Sometimes it makes sense to have synchronous function calls where one module says, I need now the map, and I can't continue until I have the map. So this is in principle similar to a pull action, but you pass on some parameters maybe. And then there might be other things that ROS calls an action that is a task that is carried out that really takes seconds or minutes to complete. For example, you can say, I need to drive to a particular location, and until the robot gets there, there might be lots of things that might be interrupting this action, and so on. So, but an action is just a higher level form of communication. So a push is a one-way communication. One node sends some data to another node. You can call this here the publisher, and this here the client or the subscriber. Pull, as I said, is the client or the subscriber wants some data, so it sends a data request, and the data provider then gives back the data. This is useful, or one problem that people found with the PR2 platform is that it generates so much data that's actually not needed, that it's not really energy efficient. You know, all of these cameras are switched on at the same time, even though there is nobody listening to it, or it in principle could happen. And so for some sensors, especially a high resolution camera, does not need to provide pictures all the time, but only when you want to read off a sign somewhere, or if you want to take a good picture of a building from above. So it makes sense to have one module that then is responsible to ask for a picture at a particular point of time. There's this publisher-subscriber architecture where the client once indicates that it needs data from somebody, and then continuously until it unsubscribes, it will get this data. This is what the typical way in ROS is. Sometimes it also makes sense to have this shared memory here somewhere, to have a central module that collects data. For example, a producer might store something like a map on the blackboard, and then another process can request data from there without having to communicate again with this process over here. This is often used for parameters, for storing parameters. Things that are so small that you don't need a dedicated process for it, but you want to collect everything, all parameters in one central place, which is easier to save and load and inspect. Good. And then there is this idea of a service call where you, where one process requests some data, maybe even has some function parameters associated with it, sending to a server, and then the server will return the result. This is also called remote procedure calls, for example. And this is a synchronous function call, even though it might be implemented as a as an asynchronous message passing. And then there are actions. As I said, an action is something that takes more time, like to navigate to a goal, and it might be interesting to get feedback during executing this action. For example, how far am I from the goal, or what is my current status? Am I still executing this? And then the server executes this and sends status updates, and it can be cancelled from both sides. It might happen that the door is locked at some point, or that the user decides that the robot should go now somewhere else because something is taking too long. Yeah, as I said, we will use ROS. If possible, install ROS already on your computer. The ROS website is really beginner friendly. There are lots of good tutorials and installation instructions there. But except installation, I guess you will learn everything necessary then in the lab course. There are some concepts. I already used these terms, so probably you don't have to discuss it in detail. In ROS consists of nodes. And a node is just a program that communicates with other programs. So a program in ROS is called a node. And nodes communicate over messages, which are data structures that are being sent over the local network or over the network. And every message has a particular topic. And so a message can be sent to a particular topic, and then other nodes can subscribe to a particular topic, and then get the data for this topic. And all the parameters are handled differently. So parameters are stored in a blackboard in ROS. But you will see how this works. And then regarding software management, ROS distinguishes between a package, which is a folder essentially that contains one or more programs, a stack, which is a logical unit of several packages that somehow have the same, that are somehow related, and then a repository contains several of these stacks, and there is typically one or more repositories per institution. At least this was the case with Subversion. Now people are moving more and more to Git, and then either stacks or packages are getting into repositories. But for us, this means that we will probably have a repository for all the code, right? For the framework that you can download. I mean, you will see all of this. Maybe it's not yet fully determined. But in principle, there will be a repository that contains all the code that you need for doing the exercises. And and then you can work inside of that. Good. There are useful tools. Makes sense to try them out, but you will do that in the lab course, tutorials. Good. And that brings me to the end. So we've looked at, I've given you a brief summary of the mobile robotics. We've looked a little bit on quadrocopters. We will look more at them, of course, in the course of this lecture. The paradigms, programming paradigms, and the programming architectures. And yeah, and that's it from my side. So are there any questions from you? Everybody's stunned. Good. So if not, don't forget to sign up for a team. You can also do it on Thursday. Yeah. Then any other questions, I guess we will see on Thursday or next week. Good. Thanks. So.